Savadi, and welcome to Module 7 Statistical Analysis, Topic 7.7, Linear Regression. At the end of this module, you have learned how to find associations between two variables, determine the strength of the association between a response variable and one or more multiple exposure or covariate variables, and how to interpret the results. Sometimes we want to know how two continuous characteristics of our population of interest are related, such as weight and height, or income versus years of education. Does one variable increase as the other variable increases? Or does one variable increase as the other variable decreases? What kind of relationship is there between the variables? Is it linear, curvilinear, or something else? A scatter plot is a very good visual tool to gain a preliminary understanding of whether two continuous variables are related. In this graph, we have plotted child's length or height in centimeters on the x-axis and child's weight in kilograms on the y-axis. Each point represents one observation of a child's weight and height in the mixed sample data. Given the shape of this plot, how would you describe the relationship between height and weight in the children in this sample? When looking at two continuous variables, we can measure the strength of their association using correlation. Correlation is a measure of linear association. Correlation takes values between -1 and +1, where -1, as you can see on the far right plot, implies perfect negative linear association, and 1, as you can see on the far left plot, implies perfect positively associated variables. Various correlation strengths between -1 and 1 are depicted in the graphs on this slide, including a value of 0, indicating only that there is no linear association. Which of these four plots has the strongest correlation? That is, a correlation coefficient closest to +1 or -1. Correlation is a measure of linear association, and it is strongest when the scatter plot shows a nice line trend, as in plot B. Plot D may also be linear, but it is not as strong of a linear association as plot B. You can compute a correlation coefficient in Stata with the command correlate, and then the two continuous variables that you would like to examine. Let's compute the correlation looking at the variable AN8 for weight and AN11 for height in children with BMI less than 40 or a normal range. When we run this command, we get a table with the variables we are correlating as rows and columns, and the correlation coefficient between each. We would expect the diagonal to all have a correlation coefficient of 1. This is because we are correlating a variable with itself. But what we are interested in here is the correlation between weight and height. So we look in the row for height and the column for weight, and we see 0.8998 is our correlation coefficient. Is this a strong correlation? Is it positive or negative? We can add a fitted line to the scatter plot we created. This is a regression line. It's the red line. The line seems to cross into the data nicely, giving a fairly strong positive correlation of 0.89. A simple regression model relates an outcome variable y and a covariate x in a linear fashion. Because the relationship between the outcome and covariate or exposure is not always perfect, we allow for some error using the Greek letter epsilon. Beta naught is the intercept of the line, or where the line will start on the y-axis. Beta 1 is the slope of the line, or how steep the line is. It is the rise of the line over the run of the line. We are interested in finding the line that best represents the relationship between the response, y, and the covariate, x. From algebra, we know that there are an infinite number of lines that can be drawn through a cloud of points. Each line here, of the different colors and line styles, represents a line we can draw through a cloud of points, representing the proportion of high school or secondary school graduates in each state or geographic region on the x-axis, and the percent of the population living in poverty in each state or geographic region, which is percent in poverty on the y-axis. Which line looks to you like it best fits the many points on the plot? We choose as the best line the line that misses the points the least overall. The green vertical lines between the points and the red line represent how much the fitted or regression red line misses the blue points. The longer the green line, the more the miss, or the greater the distance between the point and the red line. Each dot represents data for a state in the US. We call the red line the regression line or the predicted line. The green line for each data point is called the residual. Let's look at some examples closely. Based on the regression line in red, the state of Rhode Island has a residual of -4.16, suggesting that our regression model overestimated the percent in poverty in Rhode Island. However, our regression line underestimated the percentage in poverty in Washington, D.C., with a residual of 5.44. Let's revisit our data set and estimate the regression between the covariate AN11, which is children's height or length in centimeters, and the response variable AN8, which is children's weight in kilograms, only focusing on those children with BMI less than 40. Using the function regress in Stata, we get the following output. Keep in mind the order of the variable. You should put the response variable first and then your covariate or covariates. We find a lot of information in the output. The R squared is the scored value of the correlation between height and weight. R squared also denotes the proportion of variation in weight that is explained by the regression and is between 0 and 1. The higher the value of R squared, the better the regression model. The smaller the R squared, the poorer the model fit. The slope of the model, B1, is 0.208, and the intercept is -6.495. The slope B1 equals 0.208 kilograms per centimeter and represents the increase in weight for each 1 centimeter increase in height. So if we look at the equation for a regression line, y equals beta naught, or intercept, plus beta 1, or slope, times x, we can plug in the values of 0.208 for slope and -6.495 for intercept. The slope of 0.08 means 0.208 kilograms per centimeter and represents the increase in weight in kilograms for each 1 centimeter increase in height. Using least squared regression requires a few assumptions be met. It requires an assumption of linearity between the response and the covariate variables. It also requires that the residuals, those green lines showing the distance between the line and each point, or the error, have approximately a normal distribution. Finally, there is an assumption of constant variability. We will talk about each of these assumptions. We start with the assumption of linearity. This can be visually inspected looking at a scatter plot of the data of the response variable versus the covariates, or of the residuals versus the covariate or predictor variable. If the assumption of linearity holds, these plots should show a linear trend. If the relationship between the explanatory and the response variable isn't linear, the least squared regression won't work. There are methods for fitting a model to nonlinear relationships, but those are beyond the scope of this lecture. Which of these plots looks linear or close to it? Stata offers various plots that you can use to plot your residuals. You want them to be grouped close to the red 0 line. On the left, RVF plot plots your residuals against the fitted line. On the right, RVP plot plots your residuals against the predictor of child's length or height. In both of these, the plotted points seem to be linear. This slide has some complicated concepts and terminology, but the idea is simple. You can find observations in your data that might influence the model to be wrong. Technically, this plot is the plot of leverage versus normalized residuals squared. The horizontal red line is the average leverage, and the vertical red line is the average normalized residual squared. But what I want you to remember is that this allows us to determine potential outliers, or those with large normal residual squared and highly influential data points, like this one in the top left corner. Large influential points can be a sign of issues and should be removed since they might exert too much influence on the model fit and lead to a wrong model. Or the analysis can be run both with and without the very influential points to investigate their impact on the model. The assumptions of normality can be checked by looking at the histogram on the left for the residuals, or by looking at the normal quantile plot on the right. If the normal assumption is true, the dots should fall on the line in the QQ plot as in on the right. We see that although the results are not exactly normal, most of the data do tend to fall on the line in the QQ plot. So the assumption of normality might be reasonable. The third assumption of the least squared approach is constant variance, or that the values of the response variable vary across the values of the covariates. You can see this by looking at the plot of residuals versus the covariates, which is child's height here. If there is constant variance, we would expect to not see a clear pattern in the points on the plot. In this plot, we see that there is a little bit of a fan-shaped pattern in the plot of residuals versus the covariate of length on the left, and this shape is also somewhat present in the scatter plot on the right. On the left, we have the scatter plot of the data for BMI less than 40. On the right, we have the data for everyone included in the data set. We see how the regression model differs in both scenarios. This highlights the fact that outliers, bad data, or very influential data can drastically change the results of your analysis. You should spend a great deal of time ensuring your data is of good quality before you fit a regression model. For interpretation of regression results, you can say that because the slope is positive, weight increases with height. Specifically, a 1 centimeter increase in height is associated with a 0.2084 kilogram increase in weight. Since the weight of 0 is outside the range of the data, the intercept is difficult to interpret, but the intercept tells us where the line starts on the y-axis. R squared is the coefficient of determination and denotes the percentage of variation in the response, here weight, explained by the regression. So in this case, an R squared of 0.81 means that this model explains 81% of the variation in weight, children's weight in our sample, or essentially that height explains 80% of the variation in weight in our sample. Higher values are better in an R squared. They indicate that your model is a better fit. Suppose the case where we have multiple covariates or independent variables, such as x1, x2, and so on, that we want to evaluate in linear association with our response or dependent variable y. Each of these variables is measured for every participant in the sample. The multiple regression model is the same as the simple linear model, but you add each independent or predictor variable as well as the error or residuals associated with each. In the predicted multiple regression line, the slope of each independent variable is determined using a least squares approach. The assumptions of multiple regression are the same as in simple regression, but linearity should be determined for each independent covariate x and the y response. Let's take an example of weight, height, and an additional independent covariate, which is combined wealth score. We can create a scatter plot matrix in which we correlate each of the variables with one another and visualize the plots. Or we can also look at a correlation coefficient to evaluate whether there is a linear association between each of the variables. What do you notice about the correlation between weight and wealth score and height and wealth score? It appears that wealth score does not have a very linear relationship with weight and height. The correlation coefficient is only about 0.15 and 0.11, and the points in the plot are distributed all over the plot, not in a linear pattern. We can still include wealth score in the model to understand how it affects the relationship between weight and height. To perform this multiple regression, we include W score, the variable that represents wealth score, in our regression command. Now we're adjusting our measures of slope and intercept, or the relationship between weight and height, by the variable for wealth score. This gives us an adjusted equation for weight and height when taking into account wealth. We also add the command predict to tell Stata to save the residuals for our model, and then we can ask Stata to plot them. We then have a model that is adjusted for wealth score with the following equation and results table. We'll talk about the results now in detail. We interpret the results similarly when we have an adjusted regression. For height, or AN11, a 1 centimeter increase in height is associated with a 0.2069 kilogram increase in weight, adjusting for the combined wealth score. For the combined wealth score as a predictor, a 1 unit increase in the combined wealth score is associated with 0.176 kilogram increase in weight, adjusting for height, or that is, holding height constant. We still run our model diagnostics, so we make sure this is a good fit. These are our residuals plotted against child's height on the left and against combined wealth score on the right, our two predictors in the model. How do they look to you? When we do our check of the normality assumption, we plot the residuals against our leverage to find the influential data points, and we plot our residuals on a QQ plot to see if they are normally distributed. What do you think? Do you see any influential outliers? Finally, we look at the R-squared, or the coefficient of determination for the model, which denotes the proportion of variation in the response explained by the regression. R-squared can be misleading when comparing nested models, so an adjusted R-square is often preferred because it accounts for the number of parameters in the regression model. Here, we see that the adjusted R-squared is 0.8123, which is pretty good. That means 81% of the variation in weight can be explained by the model. We can also look at how R-squared changes in steps as we add coefficients to see whether an added coefficient explains more of the variability in our outcome. Sometimes your covariates can be correlated. This is known as multicollinearity, and it leads to poor model fit and parameter estimates. We can check for multicollinearity in Stata using the variance inflation factor, or VIF. VIF values above 10 may need attention. That means you might remove one of the variables from your model. You can practice on your own by building a regression model to help predict BMI using 5 to 10 different covariates. Choose the covariates based on theories or conceptual models and discuss why you chose them. Check your model assumptions, and after you run the model, talk about what variables seem to be important in your model. In summary, linear regression is a model for evaluating the linear relationship between continuous variables. There are several assumptions to the linear model, and you should ensure that you meet them. Look at your data carefully to assess whether there are any influential data points or outliers that could make your model be wrong. Interpret your results as the slope of the predictor and response variable, and be sure to report how well your model fits. And final thoughts. Remember the saying, garbage in, garbage out. Be sure to look at any outliers in your data to be sure that they are not influencing your model to be wrong. And you can now run a regression.